Okay, I guess we can start. So thanks everyone for coming. That's a relatively large audience for me. So we're gonna go over like a general introduction to protocol analysis and how the tools from formal methods can help us in this process. Hi. So for today, we're just gonna some of this stuff is gonna be boring, for some, but not for others. So I'm gonna have to go over some stuff that you already know. But if there's anything that's not clear at any point, please just raise your hand and ask me. So we're gonna go over a recap on threat modeling and crypto protocols. We're gonna see how we can model secure channel protocols and how to reason about them. Then we will look at some points of failure when porting theory to the real world. Then we'll have like a brief introduction on formal methods and how it helps us solve some of these problems that happen when porting from theory to the real world. Then we will look at two different models of analysis that we use when analyzing protocols. And finally, we'll have an intro, like a practical intro to Verifpal, a tool that I've contributed to developing. It verifies secure channel protocols, and we'll try to verify some protocols with it. So this is the generic data security slide that you see everywhere. Basically, if we want to reduce the main phases of development, we have the design stage where we define our problem, the implementation stage where we attempt a reasonable solution, and the testing stage where we see if our solution actually solves the problem. So this might be a naive observation, but from my perspective, I think most of the failures that happen are due to errors in step 1 and 3. So for today, we'll look at secure channel protocols. These are used to establish a connection between two or more parties. Sometimes it can be between a party and itself, but yeah. So the claim, any protocol has a set of security goals that it claims to achieve by the end of its execution. So during the execution, messages may have variable security properties, but at the end, the security in theory should match what is claimed by the designers. So what are the ingredients of a protocol? These are what we need to take into consideration when analyzing one. We have the principles, which is who's participating in the protocol. We have the communication channels, as in who can talk to whom and at what time or phase. Each party has an initial state, as in what it knows, what public values, what secret values, what algorithms. And then we have the protocol itself, which defines how the state is updated at each principle, and when and how, and when does a party need to perform a computation, when it has to send a message, etc. So this is an example of a protocol diagram. So yeah, as I just stated, to do this protocol, we have to perform some sort of cryptographic computation, and these are just using the primitives you all know, like encryption, decryption, public key schemes, signature schemes, etc. And then the security of the protocol is derived from the combination of these security properties of the underlying cryptographic primitives. Sometimes combining crypto primitive, like adding more primitives, does not lead to more security. So we have to carefully know where we should pick our primitives and how it should be applied and under what conditions. So this all falls into the scope of things that we need to take into consideration when analyzing the protocol. So when we model a protocol in a way that allows us to analyze it, we need to figure out what is our set of goals at the end. Do we want authentication between two parties? Do we want a message to remain secret to all parties but one? Do we want forward secrecy? Do we want any property? So this we have to think of at the start. Then we will look at how the goal is going to be achieved using the cryptographic properties of the primitives we use. We also, this is equally important to consider who we're protecting ourselves against, which is the attacker. Is it like a disgruntled employee? Is it the NSA? Is it my ex-girlfriend? It doesn't, like, it has to fall into the perspective of our analysis. So if we assume our attacker to be able to factor prime numbers, then it would be useless to apply RSA, for example. So this is equally important in coming up with our security proof. And then we will check under what conditions we are asking the questions of can the attacker break one of the goals that we're trying to achieve. So is the attacker active on the network? Is the attacker just listening? Is the attacker building a quantum computer that he's later going to use the messages that he recorded to break stuff? So this all has to come into question. So for example, this is a simple noise protocol. You don't really have to get into the details except for, so this is just an example to show like the variability of security properties while the scheme is executed. So for example, message A, this one, this is the first message that's sent in the protocol, and it does not benefit from sender authentication nor receiver authentication because there's no previous state. And then as we go along, we see that message C, D, and E, so message B does not benefit from sender authentication, but it can benefit from receiver authentication because of the values that are sent here. Then C, D, and E all benefit from mutual authentication between sender and receiver. So the security of a message kind of evolves as we're executing a protocol. This brings us to alleged security versus provable security. One second. Okay, so yeah, we can easily design a protocol. I can just say I want to do encryption here and then hash this message and send it, and there I have a protocol. But am I sure that it achieves the goal that I want? So this is usually not an easy problem because we have to take into consideration all the things that we just talked about in the analysis phase. And the more complex the goals are, the more complex the analysis can be, the more also applies to if like there's a lot of messages going between a lot of parties, it can get exponentially hard to verify a protocol. So these are some simple properties that usually are taken into consideration when analyzing a secure channel protocols, and we try to verify them at the end of the execution. So in case we reach the end, and given our set of assumptions that we had and what we obtain at the end, which is does the protocol satisfy any of these properties, then we can claim that the protocol is secure in our model exclusively, not secure period, because there's a big difference between what our model could be and the real world. So we need to be as intricate as possible when trying to classify where our analysis is happening and on what condition is it true that the attacker is unable to attack this protocol. So here's an example of a protocol deployed in the real world where it shows a catastrophe that happened due to a wrong model. So this is the protocol that's used when cars, like you would have a key fob for a car and the car, and then the way you would unlock a car is by programming a secret key on the key fob and on the car, so it's not transferred between them, it's done at the factory. And then the car encrypts unlock command, sends it over the air, and the car receives it, and it can decrypt it because it has the secret key that's correspondent. So this is kind of how the protocol happens. They know, like both parties know the secret key, they know the lock command, the unlock command, and then the key fob, which is what the user encrypts the lock command with the secret key, sends the encrypted command, and then the card checks if it can decrypt the command and if it's equal to the lock command or unlock command, and executes it if it's true. So does anyone have a clue what could go wrong here? Exactly, a replay attack. So this is apparently the case for all Honda vehicles until 2020. So this is a video of the attack actually taking place.
All right, so those are the keys. I don't have them in my hand. I talked about how you can hack into Hondas and unlock them. I didn't mention that you can actually start the engine. So here we go. And
so yeah, the attacker has complete access to the car, but the attacker did not learn the secret key. So sometimes in our model, it doesn't matter if the secret key was leaked or not. We need to see if our model represents a real-world scenario or not. So what Twen tried here is that the attacker did not get the secret key. The attacker never decrypted the encrypted command, but the attacker was able to capture the message and replay it and took control of the car. So yeah, when this protocol was designed and analyzed, probably it was the case that they did not assume that the attacker can replay a message over the air. And since this was not in the assumptions, then the protocol would have been secure, but it was not in real life. So our assumptions need to reflect the real-world scenarios. Some other problems that are not related to protocols, but we can find usually in cryptography, are implementation bugs. So, because usually the people who design protocols are not the ones who implement them and deploy them in the real world, and there's like a whole chain of people who get involved in the middle. So any small bug in the protocol can, in an implementation can just break a protocol, even if it was secure in theory. So we can look at the psychic signatures example from Java. There was this, a few months ago, there was this vulnerability discovered in Java, like the built-in signature verification library in Java, where you can just sign a value with any key and it would like consider it as valid. So this just, I mean, yeah. There's the attacks that are happening on these crypto bridges or exchanges where millions of dollars are getting leaked. There's a vulnerability in a libp2p, which is like a protocol used in decentralized networks. It was not properly validating signatures and just taking anything. There are lots of disasters where nonces were reused and then keys were derived, etc. And then there are some TLS servers which use the same key to optimize the performance. So these all happen. And other stuff that's more on the theoretical side is the security proofs being hard to verify, because usually it's written on like a paper. It's, I don't know how many pages long, and it's usually a burden for anyone who's not the actual writer of the paper to just go through it step by step and verify that it actually holds, every statement holds, every lemma is proved correctly, and then the theorem holds as in general. So we can see that some schemes were broken by our colleagues here, like Rainbow and Psych. These were, I believe that these were broken because there were errors in the proof, or the way that they were portrayed actually was not easy to audit by a lot of people, because these schemes have actually been to the NIST competition under a lot of scrutiny for years, and then no one was able to find the flaws. But then when someone just looked into it, was able to prove a counterexample and break the schemes. So it would be actually useful if we can write a proof in a way that's modular and composable, that we can use a computer to go through the steps of the proof and like affirm to us that what we're doing is actually sane. So here, all of these problems can probably solve by formal methods. So what is formal methods? Formal methods is just like applying a mathematical, like modeling our thoughts in a mathematical framework, and allows us to trace back our decisions step by step. So let's say, for example, there's a message M, and then there's a key K, and then there's an algorithm for encryption. So it takes a key, and then we can define using any mathematical framework that we like, set theory, type theory, some sort of algebra. We can define that the encryption, the decryption of with the key of an encrypted message. So we can assume that this is a logical rule. So anytime we see this thing here on its own, and we have key, we can deduce M. It's like we can look at it from different perspectives. Like it can be used using like natural deduction. So we can have like key. So we can look at it in different perspectives. But what this allows us to do is to model our thoughts using mathematical properties, and then use what this, using mathematical frameworks, and use what this framework allows us to do to prove our thoughts or prove our hypotheses. So this allows us to abstract our verification process, steps in our verification process. So, for example, someone can just build a library, verify a whole bunch of stuff, and then we can just use this library as if we use a code library to use their proofs to write proofs on top of them and verify our own statements. So this allows us to not have to reinvent the wheel all the time. So particularly in cryptography, these, I kind of went through that. So, and a big example of applications of formal methods in cryptography is its use when in the development stage of TLS 1.3. So there were a lot of bugs that were being found progressively with previous versions of TLS, like 1.1, 1.2, and then now we're at 1.3. So the designers decided that, okay, we're going to employ formal methods in the design process and try to rule out classes of bugs using these tools. And then we can expect that our protocol will have a much longer lifespan because of the guarantees that can be provided by formal methods. So this is kind of like a landscape of formal methods, like the Russian dolls that can go into each other. So we have mathematics as a whole, like the mathematics we all know. And then there are general purpose formal methods tools that we use in computers. That, like, these are programs that have at their kernel the mathematical framework that we're employing, and proofs about proofs about the framework itself, so that it relates to what we know in real life. And these tools can be theorem provers like COSIC or AGDA or Lean. We have stat solvers. Sometimes these are used for Boolean circuits. There's a lot of tools. And then under these, if you go a level below, we have the computational model and the symbolic model. So the computational model is a step further, that some of these tools, for example, like SSProof and EasyCrypt, they are an extension of a theorem prover called COSIC. And then they use whatever the guarantees that COSIC provides to go further and help us analyze crypto protocols. And then we have the symbolic model, which is also like an abstraction, but it's not necessarily using these tools under the hood. It just, so as we go from here to here, we have relatively easier tools to use. So these tools here kind of grab you by the hand and guide you through the process of verification, while these tools give you more freedom to actually implement what you want. So yeah, we can define a finite field here and use it, but not here. So yep. So these tools are what we're gonna basically look at, and we're gonna focus on the symbolic model for this talk. Yeah, so ProVerif uses a mathematical property called, a structure called horn clauses, and then it uses something called the applied pi calculus. It's, I think it's an extension of, it's similar, very similar to lambda calculus, but it models messages as processes, and like it has a way to encapsulate the whole execution of a protocol, from creating the messages to modeling the principles at hand to modeling the primitives in a way that we'll see now. And then we can ask questions at the end of our verification to see whether security properties hold or not. Yep. So also, to use any of these tools, these are kind of self-contained. You don't need to learn how the math works underneath. You can just use it as a independent thing. So let's talk about the symbolic model a bit. In the symbolic model, for example, when we assume an encryption function, it's kind of like it is here. We don't care if AES is used or RC4 or whatever mode. In the symbolic model, we assume that the primitive is perfect. So giving this, like a ciphertext that's an encryption of M using K, it is literally impossible to recover M if you don't have K. This is like a assumption, and then we build on top of that. The same is for public key, like using the public key crypto or signatures, etc. So in these tools, you're kind of, in some of them, you're limited to the primitives that the author of the tool have implemented themselves. In some of them, you can also, like, so in Verifpal, this is the case. In ProVerif or Tamarin, you have you have like a limited way of defining a primitive. So it would be, like, you could define encryption, and then you could define a function for decryption that does this. So it just compares, if the keys are the same, it gives you M back. So these are used to execute the protocol symbolically, and then teach the attacker some methods of interacting with the execution of the protocols to try to infer knowledge and break the protocol, essentially. And the computational model, things are more intricate. So some of the tools like EasyCrypt or SSProof, they employ something called a probabilistic logic framework. So it's called, for example, for EasyCrypt, it's called probabilistic Hoare logic. So over here we can implement, for example, elliptic curve Diffie-Hellman, and then prove that recovering secret keys from public keys is as hard as solving the elliptic curve discrete logarithm problem. So we can calculate the probability, not calculate, but we can prove that the probability of doing this is really close to the probability of solving the problem. Here, we actually care if we're using AES, for example. We care if we're using El Gamal or RSA to sign messages. So we can actually implement the things we want and prove properties about them. But equally, everything that we can prove here, we can prove using the computational model. And everything we prove using the computational model, we can go back and prove it using other ways. So if we obtain a result in the symbolic model, we can be sure that we have it in the computational model, and so on and so forth. But, so yeah, here's a quick comparison between both. The symbolic model can be actually fully automated. So you can just write your protocol design, as we'll do in a bit, and then run it, and then it will come back with a result. Whereas here, you have to, like you do in a real security proof, you have to write hypotheses and then prove them, and then you have to interact with the computer to prove these statements. So, and then at the end, when you prove everything, you can be sure that you got your result. So you can actually do game-based proof, you can do UC, and in some cases, you can actually, if you actually implement everything that is needed for your protocol, you can actually end up with an implementation that you can execute. So you can define your whole MPC scheme and then use a compiler from COC to OCaml and then obtain executable code that you can be sure that it works because it relies on the kernel of trust that COC has. So it follows a series of mathematical deductions. And as I just said, if there is an attacker in the computational model, then there would be an attacker. I think it should be the other way around. If there is an attacker in the symbolic model, for sure there is an attacker in the computational model. Actually, no, this is true, but this is this took a lot of time to prove. It's a paper called Computationally Complete Symbolic Attacker. Yeah. So the computational model just seems better, so why not just use it for everything? So if we want to define and use Shamir secret sharing in Verifpal, we can see that we already have this is the whole file. We already have a function in Verifpal that does Shamir secret sharing. So it splits a secret key into 3 shares. So over here we define like the state of attacker, whether it's active or passive. We'll talk about that in a bit. So we just do this, and then we can verify it, and it works. Like, is the secret key confidential if Alice leaks S2 over a public channel? It says all queries pass, so yes. Whereas if we want to do like 1/3 of that in EasyCrypt, so it's kind of intimidating to look at. And kind of takes us back to the problem of like verifying proofs manually, like the ones on paper. So yeah, now we'll go through like an introduction to Verifpal, and we'll try to do some interactive stuff. So it's an intuitive language for modeling protocols. It doesn't let users make errors because it puts users in a sandbox. So you can do a lot of things with it. You can verify signal with it. You can verify TLS 1.3, etc. But it gives you a lot of constraints. So the attacker, for example, can be two things. He can be an active attacker or a passive attacker. And these passive or active kinds of attacker are predefined by the authors of the software. So a passive attacker can just look at the messages that are sent over the network, and he cannot interfere in any way. He cannot replay. Actually, he might replay after the protocol execution, but he cannot do a man in the middle or these sort of things. The active attacker can have like parallel executions. He can intercept a value during one execution of a protocol, modify it, and then create another instance of the execution of the protocol, and try to infer values out of that. So we'll see these in a bit. There's an extension for Visual Studio Code, and we'll see all of this stuff. So, yep. It can like analyze forward secrecy, key compromise impersonation, all of that stuff. But it does not produce proofs. It helps you with analysis, but it's not formally proven to miss attacks. To not miss attacks. So ProVerif is another tool in the symbolic model which is proven to not miss attacks because it uses the horn clauses that we just talked about. So if an attack exists, verifpal might miss it, but proverif won't. The difference between both is that verifpal is much easier to use, and it can actually compile to proverif code, so you can start modeling your protocol in verifpal, and then once you're sure about the design you have, you can compile it, and it saves you a lot of effort and boilerplate that you have to write when designing, when modeling a protocol in proverif. So this is also the case for COC. We have modeled the passive attacker in verifpal in COC, and the attacker analysis for verifying confidentiality queries in that language, and then we wrote a compiler that just converts a model from verifpal to COC. We'll see a demo in a bit. So it's more towards people who want to start verification, and this does not mean that the results are kind of useless, because this was applied in the real world with companies like Zoom and Google, and these people were able to find attacks in their protocols using a short amount of time, like in a day or two. They were able to model their protocol and find attacks, and otherwise it would have taken them like weeks or months to do that in proverif. And if they wanted to do that in the computational model, it would have taken them a lot more time, because you have to write stuff like that. So it helps you to rule out classes of attacks before spending more time verifying protocols. So this is the language. Like, you have blocks like this one, and then you can define principles and blocks where, for example, generates a fresh random value A, and then computes the public key, which is G to the A. This is Alice, and then Alice sends a message to Bob, which is this public key, and then Bob knows a private value M1, he can generate B, just like Alice did, generate a public key, and then do AED encryption using these three values, etc. So you can write this in verifpal, and you automatically get like a protocol diagram that shows you that what you did is kind of works. And if there's like something that doesn't make sense in your protocol, it has like a checker that just allows you to like, it shows you like, hey, you made an error here, check if you actually have this value before using it. So yeah, as we said, primitives are built in. It's a feature, not a bug, because we actually want to help people start getting results rather than spend a lot of time in a process that's prone to bugs and kind of counterproductive. So it's never going to be better than the other tools, but it's just it has a different purpose. It has something called checked primitives. So for example, yeah, so this GC here, it has like brackets around it. This means that, for example, the attacker, even if they were active, they cannot modify this value. So it's kind of authenticated between the users. So it has some advanced features. We can have like temporal logic to define phases, like this thing happens before this thing. And for example, at this stage, a value is leaked or revealed to the attacker. They hack a phone, they get it. It's like the case for forward secrecy. It has unlinkability queries, so we can check if a value can be linked to another value. So in case that value is leaked, do we learn anything about, like if value A is leaked and A is linked to B, then we learn some stuff about value B. It has freshness queries, which means like, is the value randomly generated every time? Model passwords, these are like, we can brute force these values, and we have preconditions. So if, for example, a signature doesn't check out, then the protocol stops, and this stops the attacker from doing sort of things. So yeah, we'll take a look at this stuff. Yeah, we have some time. So yeah, that's the transpilation that I've talked about. So yeah, if you want to look at the tools, this is verifpal, and then this is proverif and cryptoverif in Tamarind. This is fstar or coq or that sort of stuff. These are like very general purpose relative to what we're trying to do. Yeah. So these are like companies that use VerifPal, the ones we can talk about at least. And yeah, let's do a demo. So let's say we have this protocol. It's very simple. We're going to try to verify it using VerifPal. So Alice has a secret key A, Bob has a secret key B, and Alice knows the public key relative to this one, and then encrypts a message, which is the key, like the long-term key, using the public key, and sends it to Bob. We want to see if an attacker might be able to recover K in some way. So 1 second. So we just create a file. And this is using Visual Studio Code with the extension already installed. So let's start with a passive attacker. So we can define a passive attacker just like that. And then we can define a principal, Bob. Bob knows a private value, which is a secret key. He generates the public key relative to it by doing like g to the power the secret value. And then let's say that principal Alice exists, and then Alice generates the secret key that's a long-term key. So what happens is that Bob needs to give Alice his private key, otherwise Alice wouldn't be able to encrypt it. But let's assume that they've sent this over an authenticated channel. Or actually, let's not. Let's just say that Bob sent his private key in the air, unencrypted or over an unauthenticated channel to Alice. So we can send a message this way. Bob sends a message to Alice, and it's the public key. And then after this line, Alice, it's as if Alice has this knowledge in her state. So Alice can perform operations using that. So she's gonna encrypt this key and send it to Bob. Let's say this is a ciphertext, or that's a message. Encrypt of using the public key of Bob, and then that's the whole protocol. So she sent that. This is literally equivalent to what happened here. So then at the end, we want to check if an attacker would be able to learn key, the value K. So what we do is we just define a queries block at the end where we ask questions. We ask VerifPal to give us whether K is confidential by the end of the protocol. Okay, and that's it. So what we can do is then go to the command line test and try to verify this. So a passive attacker should not be able to recover the secret key because it's public key encryption. The attacker does not have the secret key that is required to decrypt K. But yep. Thanks. So it's secure because we didn't send anything. But now if you try, it's not secure. Can anyone guess why? Let me just remove this because we don't need it. So it's a passive attacker. It cannot, oops. Were you able to see before? So, yeah, this is gonna be weird. So it says that K is obtained by the attacker. How is that possible? Let's see the protocol model. And this is a thing that actually happens in real life, where you think it's correct and then it's not. So I'm gonna just save some time and tell you why it didn't work. It's because we use symmetric encryption instead of public key encryption here. So if we use public key encryption instead of symmetric encryption, and we verify it, oh, hold on, I didn't save. It's now safe. It's like all queries pass, so the K is confidential. So these things, the modeling errors, these happen in real life where people spend weeks trying to verify protocols. For example, a popular one was at Real World Crypto of this year, where some people found a bug in the ProVerif model of the Swiss electronic voting protocol, and then they discovered a huge flaw in the protocol that was previously deemed secure, and it was about to get deployed. So errors in the protocol can happen, but if you don't spend like weeks trying to define this, then it's okay to make an error. You can detect it, and it's easy to trace back everything that you've written. But if you have like a very, very large model, it gets harder and harder. But we can also like check some other protocols. So for example, this is Firefox Sync. Oops. So this is kind of like a more complicated protocol. This syncs the state of like tabs and passwords that are stored in the browser between an instance of Firefox and another on another computer. So we can model this entire protocol in like 50 lines of code. The equivalent of this in ProVerif, which I don't have because it's classified, is like around 600 to 700 lines of code. And you can get the same result at the end. You ask the same queries and you get the same results. It's just that in ProVerif, you're sure that you're not gonna miss an attack. But here, if this catches an attack, then you've already saved a lot of time trying to implement it in another language. But like if we don't know anything about the protocol and we can just read what's happening, someone can just kind of make sense of what's going on. It doesn't need a lot of effort. So like it has a very small set of things that the user can do. So yeah. Now I will show you how a protocol can be compiled to another framework like COC and how we verified things in COC. So this is a protocol where Alice knows a public value C0, that's like a parameter, generates a secret key A, and then the public key corresponding to it. And then Bob also knows that C0, he generates two secret values, M1 and B. He generates the public key relative to B, and the Diffie-Hellman key exchange between Alice's GA and his secret key B. So this is public key, this is the private key. And you can do Diffie-Hellman just like this. And then he encrypts, like uses AAD encryption to encrypt M1. So the signature of the function is just like key, message, additional data. So C0 is the additional data used for the AAD algorithm. Then he sends E1, which is the ciphertext, and GB, which is this public key. Alice does the Diffie-Hellman from her side and decrypts this value, and then at the end it checks so this question mark here is for checking whether a thing is valid, like it was decrypted in a valid way or not. So if it were like sent by an attacker who does not have the proper key, and Alice was trying to decrypt it, it would get an error like this is not encrypted with the correct key. instead of getting garbage. So the protocol execution stops, and then the attacker would not be able to do stuff on top of that. So this is the model in VerifPal. We can run it here. And all the queries pass. Actually, let's take a look back here. This is the first protocol that we... yeah, I'm sorry, I'm just gonna take you back to this guy to show you some other features before going to COC. So let's assume that we made the attacker active in this case. He can do man in the middle, he can do some weird stuff. So, oops. Yeah, so now, I'm sorry if there was a context switch. Is everyone okay with this, or do you want me to? Okay. So now if we have an active attacker who can do man in the middle, we can see that K can be obtained by an attacker. How? It shows you that PKB, this value here, it can be mutated by the attacker into any value that he wants. So we just say that this is G to the nil. And then the message instead would be G to the nil, like encrypting K with G to the nil. That's the message that's coming from here as a result of the attacker sending the wrong key. So here, Alice would encrypt with the attacker's key and then send the message. And then since the attacker has the secret key, he can decrypt it and obtain K. So if we had an authenticated channel where Alice is sure of Bob's identity before the execution of the protocol, this could actually be a safe protocol. And this can be modeled by just adding brackets around PKB, which means that PKB is a value that's pre-authenticated, sent on a pre-authenticated channel. Let's say they have TLS between them. And then we try to verify now, and then the queries pass. So it's easy to switch like assumptions that we have and test around and see what makes our protocol safe. We can do some modifications in a couple of minutes and see whether our hypothesis holds or not. So let's go back to the other thing. So this already we tried it and it passed. So let's try to compile this protocol to a COC model. So we do just verify, translate this, and then, yep. Sorry? Oh, so this was just, so G to the nil is, we assume that the attacker's secret key that he's always going to use is nil. And then G to the nil is the public key of that. So it can be actually any value. It's just a decision we took when doing this. So if there were multiple states, there would be G to the nil 1, G to the nil 2. It's just an arbitrary value that the attacker decides. No, it's a weird name, but it's just something that the attacker knows. So maybe it's a good idea to change this. Yeah, it's not 0. Okay, so we're gonna compile this to COC. So we're just piping it to a file. Oops. Oh. I'm using the wrong directory. Okay, so now we have this. So this is the whole, like this is, so these two things lead to the same question at the end. We're asking for the confidentiality of M1. But if you want to do it in a way that's with high assurance, we have to, I will show you, we have to, yeah. So for example, this is a lemma for the correctness of public key encryption. So, oh, actually, this is commented out. Sorry, just a sec. Okay, so for example, this is how we define construction. We defined, this is previously done, that nose is like a thing. So nose, the equivalent of nose k is that the principal that's going to use this function has k in their state. So this is like function programming. So it takes two variables and it returns. Yeah, so if the attacker, if anyone knows k and an m, they can obtain a constructor for a primitive, which is the encryption of k and m, and they know that value. And then to decompose it, we say that if they know k and c is this exact thing where k is the same value that they know and c is this, then they know m, just like we did here. This is a very simple example. So we define this for all of the primitives that we use, and then we define how the attacker can use these values, and how the states are defined, and how like what it means actually for the attacker to obtain a value. And then at the end we can start the verification. Oh, I need to switch. It starts from scratch. We did that just because using the frameworks, we found that kind of counterproductive because we wanted something very simple. I can discuss that with you later if you prefer. But this was a decision that we had to take. So when we verify something in COC, we have to like go through each statement, and then it literally runs a proof. So if we have this statement here, we have two values. We prove that these two values, if we concatenate them, then they are in the form of concat 2ab. So we literally have to prove every single statement in the whole algorithm, and then we obtain our answer here at the end. So I need to clear this. How do I clear this? Okay, because I've run this before. So here is the protocol execution. So for example, the Alice knows public C0 generates A. This is the protocol execution. And then at the end, we ask for confidentiality, and it would tell us that, yes, this value is confidential, which means that in everything that we defined, the attacker was not able to recover the value. So that's mainly everything I wanted to talk about.